All right, so that's, I think, all you need to know about independence. And now we're going to talk about conditional independence. So, like we said, independence means that knowing something about one random variable doesn't actually tell you something about anything about another one. Now, sometimes that kind of relationship can be the case only after you know a third thing. So, for example, let's say we're considering a cup of tea, and we're asking about the temperature of that tea and whether or not it's bitter. It may not be the case that the probability of it being bitter is independent from the probability of it being hot or cold. And so the reason for that might be, let's say, if you oversteep it, right, or if you make the water too hot, that might oversteep it very quickly and it'll be bitter. And so that's the case where clearly the temperature of the tea is kind of influencing the bitterness. And so these things are not going to be independent. But perhaps they are independent if you condition on a third variable, which is how long it was steeped for. So how long the tea was steeping influences both how hot it is after it's been steeping and also how bitter it is, right? So it may actually be that a colder cup of tea is more bitter because it's been left longer, and a hotter cup of tea has not been steeped as long and therefore is less bitter. And so if that's the case, and really it's just time, it's how long that this thing is being steeped for that is influencing both of these, determining both of these variables, then it may be that if I know how long something has been steeped for, then in that subpopulation of cups of tea, then the distribution of y does not matter if I also know x additionally. So this is called conditional independence. And maybe I have a better. Okay, let's stay here. So the idea is that, think of this time. So let's say I take the subpopulation of cups of tea that were only steeped for 5 minutes. So among cups of tea that were steeped for 5 minutes, the amount of bitter cups of tea is the same as the amount of bitter hot cups of tea, and is the same as the amount of bitter cold cups of tea. So it's really the steeping time that is relating these two things. So that's the definition of conditional independence, and we write it like this. So we say y is independent of x given z. That's how it's often read, but I would encourage you to think of this as y is independent of x in all subpopulations of z, or in all strata of z. That's really, I think, a more intuitive way. So that's what's written here. So within each stratum of z, we have that y and x are independent, where the independence of y and x is just the standard definition that we are already familiar with, that knowing x doesn't give us any information of y. It's just now that knowing x doesn't give us any information of y as long as we already know z. If we don't know z, they may not be independent. Because why? Because knowing x could tell us something about z, and then z therefore tells us something about y. But if we already know z, then these things are independent. That's conditional independence. So conditional independence is useful in terms of factorizing things the same way that marginal independence is useful. Because let's say we have a distribution of 3 random variables. Again, in the previous lecture, we saw that we can always write such distributions as products of factors of conditional distributions, where we're progressively conditioning as we go from the marginal to the left. We're progressively conditioning on more and more things. And if you have such a factorization, and let's say in this example, we know that y and x are independent given z, then these two probabilities are the same. And that's the definition of conditional independence. And so this factorization simplifies a little bit. So we don't have to condition on x over here. We can just write y given z, and here it's x given z and probability of z. All right, so let's go back to an example that we looked at the beginning of the lecture, which is that we were asking, is winning the lottery independent of college education? And perhaps paradoxically, we saw that these things are not independent. If you can go, I'm sure, if you go, I actually haven't looked at this, but I'm sure if you go and look at survey data, get the US population, and you make a big table, and you say, did this person win the lottery, yes or no? And then did this person have college education, yes or no? I guarantee you, if you look at that pattern of data, you're not going to get the same marginal probability of college education if you subset to the people who have won the lottery. So those are not independent. Again, it doesn't say anything about causality. It's just the pattern in the data. Now, my next question is, conditional on playing the lottery, is winning independent of college education? So here we're subsetting not to the whole US population, but to people who play the lottery. So if you want to help yourself think about this a little bit more rigorously, again, it kind of helps to imagine the data table where if you actually went out and surveyed everyone. So here's all my people in the US. And we asked them, let's say, did you go to college? We asked them, have you won the lottery? And then you ask them, did you play the lottery? Okay, so we're going to look at this last column last, but let's say that these are going to be mainly zeros, right? This is a very rare event. And then here, something like this. So this is the table you have to imagine. And we know that if you just subset to the people who win the lottery, you're going to get more zeros here than if you look at this column as a total. Now the question is, conditional on playing the lottery, is winning independent? So here I'm saying, if I first just condition on the people who are playing the lottery, so I get rid of everyone who never played. Okay, just looking at that subpopulation, is winning independent of going to college? And there, the answer must be yes, because winning the lottery is totally random. It depends on nothing, right? It's just basically a coin flip. And so the people who are playing the lottery who have gone to college have no higher chance of winning than people who are playing the lottery who haven't gone to college. In other words, the probability of win given college, in the subpopulation of college goers, still in the subpopulation of people who are playing the lottery, is the same. You have the same chance to win if you don't have college. So I should put college equals 1, equals 1. Be strict here. Given, sorry, my ones look like the conditioning. Given that college is 0 in the population of people who are playing. So this variable, knowing college, gives me no information about winning as long as I already know about playing. Okay, and indeed this implies, so by using the rules of conditional and joint probability, you can calculate and show that these two will be equal to just the marginal probability of winning, given, so if those two things are equal, then they also equal the probability of winning just in this subpopulation of people who play, right? Again, intuitively, let's say that like 1 in a million people who play win, right? 1 in a million people who go to college who play win. 1 in a million people who don't go to college and play win. So these probabilities are all equal, and this equality right here again is what defines that win is independent of college given play. Oh, sorry, given play. And I like to put the parentheses. I think that makes it conceptually clear, but often you'll see it without as well.